So we are discussing feed-forward neural network, which is the basic structure of neural network and deep learning. And like with other types of models, so like we have discussed logistic regression, the key operation that we want to understand and study is how to make a prediction and how to train the model based on the data. So in order to discuss how to predict something based on input data, well, let's imagine you have a defined structure and that comes with the weight. So in order to represent a model, you need a structure and weight. So let's assume both structures and weights are given, and provided that, let's try to discuss how to use the model to make prediction. So prediction is easy. So say you have two input variables, you provide the x1, x2 value, and they are going to get aggregated using the weight defined by the model. So let's try to think from here. So in order to make prediction y, that is the outcome of f6, and f6 is built by w2, w2, 2, well, let's say in this way. So f6 is defined by the value of f4 and f5, something like this. And there are some kind of recurrent structure. So f4 is defined by the previous layer. f5 is again defined by the previous layer. So let's take a look at f4. f4 is a function, so e is sort of placeholder in this notation, but e is essentially representing this. So f4 is the function of w114 multiplied by f1, w124 multiplied by f2, w134 multiplied by f3. So it's going to be the collection of the signal goes through this connection. And again, itself has an activation function in it, so f4 includes an activation. And then let's take a look at f1, which is one of the input to f4. f1 is the function of x1 and x2, the original input. So you have two weight value. So w011 multiplied by x1, w021 multiplied by x2. That defines the input to f1, and f1 also has an activation function. So you will see things are cascaded in simple operation. So x1 and x2, the original input, aggregated and activated. And each of these units at the first hidden layer, they are defining certain output based on the input value, and they again handed over to f4 and f5. And they go to f6 and so on. So this is how you make a decision using feed-forward neural network. And basically using this analogy and this vocabulary, well, you can sort of summarize the behavior of a feed-forward neural network in this way. So you're providing some signal to the network and you process it to hand it over to the next layer. In the next layer, you receive all the signal, process it, hand it over to the next layer. So you're basically feeding signal along with the network. So you're feeding forward the signal along with the network. So that's why you are calling this model as a feed-forward neural network. So prediction is quite straightforward, so nothing should be really difficult in this context. And let's talk about the learning side of the neural network. So this is the problem that hasn't been solved for 40 years. Well, to spoil the answer, you are using what we have studied. So we are using gradient descent. So basic idea of gradient descent is where you are taking the gradient from your loss function or objective function, and that is multiplied with the learning rate. So learning rate control the speed of update or rate of weight update. So you have this quantity, so alpha multiplied by the gradient, you basically get the subtraction to the current W value that will yield the next updated W value. But the problem is in the previous network, you have multiple W. So you have bunch over here, you have another bunch over here, and you have another bunch over here. So how to achieve this is not straightforward problem. So the idea is backpropagation. So backpropagation is you're going to take one backward sweep from the output of the network to the input to the network. So running is essentially updating the weights. And what you can measure is the loss function. So you're going to estimate the loss function at the end of your network. And you want to measure the effect of each layer and effect of each weight layer by layer from the back to the front. And the goal is the same. So you still want to minimize the objective function or error function. So this diagram is illustrating the error estimated at each layer. So say where you have ground truth and compare your outcome to the ground truth. That will give you the error.
So here delta in the diagram represents the gradient of the error.
And this gradient were made from the aggregation of F4 and F5. And each of these connection represents some weight value. And here is the important part. So you have the gradient of the error in a aggregated form.
And we want to send back the gradient of the errors to the previous layer in accordance with the current values of W.
Where contribution of F4 to the error, that is determined by W over here. The contribution of F5 to the error was determined by W2 here. So what you want to do is, we're considering the value of W21 here, W22 there. We'll try to sort of correlate the error
to the previous layer.
So according to the current value of W21 and W22, you can determine the gradient error that are responsible to F4 and F5. And you're basically repeating this process. So at the position of F4, you have error that you are responsible with. So delta 4. And each of these are coming from F1 and F2 and F3. And one thing we know is the current set of weight value. So by considering these weight value, we can sort of distribute the error in terms of delta 1 and delta 2, delta 3. Well, the important part is now delta 3, for example, is not only determined by delta 4, but also determined by delta 5. So in order to calculate delta 3, you want to consider both W34, which is here, W35, which is here. And you are considering delta 4 and delta 5. So this is illustrating the basic idea. And the idea can be summarized in this way. So you want to figure out how much each node contributes to the error. So if you take this process, where you can calculate all of those delta, so delta 1, 2, 3, 4, 5, and based on those computed delta, we can write the update rule again. So the one in the rectangle is what we have seen so far. So here, eta is the learning rate, and delta is the error that are responsible. And you are also considering the input data. So based on the error that are responsible to, and you're considering the data and aggregate them with the running rate, that will decide you how to update your current W. By the way, running rate is determined by the user. So this is the basic idea. So this is